Hello everyone, welcome back to this course. In this lecture, we will explore how Node.js works under the hood and why it is considered one of the most scalable and efficient server-side technologies. Of course, when used correctly, we will dissect Node.js internal architecture, uncovering how it handles operations through components like event loop, event queue, and thread pool. Also, we will see what makes it ideal for high throughput IO or input output based applications. Okay, before we delve into the internals of Node.js, it's important to understand the architecture that is employed by the traditional server-side technologies. As one can see in the current slide, technologies such as PHP, Java, or let's say .NET, they generally follow a multi-threaded model. In these systems, each incoming request is assigned a separate thread from a pool, and this allows concurrent handling of multiple requests. But this, of course, comes with a significant drawback. Uh, there is a limit to the number of threads that the server can handle concurrently due to hardware constraints, or more specifically, due to memory and the CPU constraints. Once all the threads are occupied, then any additional incoming request that arrives at the server must wait for one of the threads to become available, leading to latency and degraded performance under heavy load. Now, how Node.js addresses this limitation? It addresses this limitation using a completely different approach. It operates on a single threaded event driven model, which is exceptionally efficient for IO bound tasks. This architecture allows Node.js to handle thousands of concurrent requests without creating a thread for every single one. So let's start examining the internal design of Node.js and see how this efficiency is actually achieved. Now, this slide presents a high-level overview of Node.js architecture. At the entry point of any Node.js application is the JavaScript engine, specifically the V8 engine that is developed by Google. This engine is responsible for executing JavaScript code. However, it's important to note that the V8 engine alone cannot handle operations such as disk I/O, network access, and some cryptographic related operations, because these are system level operations and V8 is solely designed to execute JavaScript. Another thing to note here is that now modern web applications frequently involve operations that fall outside the JavaScript runtime. Uh, Operations like accessing databases, performing file operations, resolving DNS queries, or executing CPU-heavy cryptographic calculations. Uh, these are some non-JavaScript operations and require native system-level functionality. Now, to handle this, Node.js introduces a very powerful component that is known as libuv. Now, what is libuv? Libuv is a cross-platform C library that serves as the backbone for this asynchronous input-output model in Node.js. It actually acts as a bridge between the JavaScript engine and the operating system, enabling the asynchronous execution of tasks that cannot be directly handled by the V8 itself. It also manages the event loop, the event queue, and a built-in thread pool. We will talk about this thread pool in more details going forward. Both the V8 engine and the event loop. So this is the component that is responsible for monitoring and dispatching the asynchronous tasks. They operate together on a single thread. It is often referred to as the main thread. This is the central execution thread of a Node.js process, and it's crucial for maintaining the non-blocking nature of Node.js. Since there is only one main thread, ensuring that it remains unblocked is the key to the scalability and the responsiveness of the application. The thread pool that is provided by libuv, it by default contains only 4 threads, but this can actually be resized based on the system requirements and by tweaking some configurations. Its primary purpose is to offload blocking and CPU intensive tasks, allowing the main thread to remain free for other operations. Now let's understand this architecture flow in more details. So what happens is whenever an application or this Node.js application receives a request, the JavaScript code handling that particular request is executed by the V8 engine. Now, if the code contains a non-JavaScript operation, now what could be a non-JavaScript operation? It could be a file system operation, it could be a network call, it could even be a cryptographic based operation, right? So such operation is actually passed to the Node.js bindings. This acts as a intermediary interface between the V8 and the libuv. Now, the Node.js bindings here determine how the operation should be executed. If the operation is synchronous, uh, that it could be a file reading operation that is performed in a synchronous manner. We will read more about or understand more about these methods going forward into this course. Such operation, for example, reading file in synchronous manner, it is executed by making a blocking system call, which means the main thread will be halted until the task completes. And during this time, no other incoming request can be processed, making it a bottleneck. That means Node.js server will be busy, performing this blocking or synchronous operation and will not be able to handle any other incoming HTTP request to the server. This is why synchronous methods are discouraged in production grade Node.js applications. However, if the operation is synchronous, now the asynchronous operation could be the same file read, but performed with a different function. It is queued in the event queue, which is constantly monitored by the event loop. We can often even refer to event loop with the name, say, the main thread. The event loop checks for pending tasks and picks them up for processing without blocking the main thread. And this is the heart of the Node.js non-blocking architecture. Now, there could be two scenarios that can occur whenever the event loop picks up a task. The first scenario is that the task that the event loop just picked up is a CPU intensive task. Now, if the task is something like a DNS lookup, image processing, or cryptographic based computation, in that case, it is offloaded to the libuv thread pool, and these background threads will handle the task and notify the event loop once the task is completed. And since the thread pool has limited capacity, too many CPU intensive tasks can actually saturate it and create a backlog. Okay, hence Node.js is not ideal for CPU bound workloads unless additional measures like worker threads or you could say more threads are introduced. The second scenario could be that the task that event loop picks is an IO intensive task. And if the task, let's say involves a database query or probably a network call, then it does not even go to the thread pool that is provided by libuv. Instead, it is handed off to the operating system's IO management tools. Those IO management tools could be ePOL on Linux operating system, or it could be even KQ that is available on Mac OS. Now, what are these? These are actually some kernel level IO multiplexing mechanisms that watch multiple file descriptors to see if any of them are ready for reading or writing, something like that. Okay. Then these mechanisms, ePOL, KQ, etc., they are far more efficient if you compare them with the traditional polling mechanism. Rather than periodically checking the status of IO operation, which of course wastes multiple CPU cycles, which typically happens in polling process, what they do is they notify Node.js once the operation is completed. And at that point, the completed task is pushed to the event queue, from where the event loop can pick it up and can resume its execution. Now, this event-driven approach is extremely efficient and reduces CPU usage significantly. To tie it all together, suppose you issue a database query, to your Node.js application, then this query is going to be handled by something known as the database driver. Now, that database driver, the example could be PG in case of PostgreSQL. Okay. What will it do is the Node.js will internally utilize ePOL or KQ like mechanisms to monitor the connection. Now, once the database responds, the OS informs Node.js that the data is ready. Meanwhile, the event loop remains free to handle other requests, ensuring that your application remains non-blocking and highly scalable, even under root. Okay. So in summary, the architecture of Node.js relies heavily on a single-threaded event loop, a non-blocking I/O model, and a background thread pool for executing system-level or CPU-heavy tasks, which is provided by libuv. Now, this design works brilliantly well for web applications that require high concurrency and frequent I/O based operations. The examples could be API servers, real-time chat applications, and even the streaming services. However, it's important to emphasize that Node.js is not well suited for CPU intensive workloads unless you explicitly manage those workloads using worker threads or probably a slightly different approach, which you can refer to as the microservices approach. Avoiding synchronous methods in production code is also crucial as they block the main thread and undermine the very advantage that Node.js offers. Now, while leveraging asynchronous programming and understanding Node.js architecture, you can build web applications that are not only fast, but also scalable as well as resource efficient. Now, what we are going to be doing is we will revisit the simple HTTP server that we built in the previous lecture, and we will try adding a CPU intensive operation to demonstrate how a synchronous code can actually block the event loop and can significantly impact the application or the Node.js application. So in order to try out all that, we shall navigate to our VS Code window. Okay, so this is the server that we used in the previous lecture. Okay, here we could see that there are about 3 routes or paths implemented: about, contact us, and profile, and each of this route is doing certain things. What we did in the previous session is we also used a tool called Thunder Client in order to check that if our server is behaving as per the expectations, and it was behaving. Now, what I am going to be doing here is I am going to be adding some synchronous operations, which is going to block this Node.js server for other incoming requests that this server receives. And let me quickly add that code. So what I'm going to be doing is I am going to be adding that code, say, in profile section. So I will add that code here. So what this code is actually doing is this is computing the hash using this function called pbkdf2 sync. Please note this sync keyword appended to this function name. This represents, or this indicates, that this is the synchronous version of this function. That means it is going to perform this operation in a blocking or synchronous manner. Now, since we are making use of this crypto, we have to make sure that we also import this crypto module, just like we have imported HTTP. So what I'm going to be doing is I am going to be writing a require call for this crypto function or this crypto module here. Now, what it actually does is, this is running a loop. This loop is going to iterate for 10 times, and 10 times we are going to be computing this hash, and each time we will see that how much time does it take to compute each individual hash. Let me just run this server and show you that how this endpoint is going to be behaving. So I will open terminal. And here I would say, npm run start. This is the command or the script that we have even specified in our package.json, which says start our application. So once I do that, my application will start running on this particular port, that is 88. Now I shall go to this Thunder Client extension here, and I will navigate to this profile. And the moment I click on this send button, then you could see that it is computing these 10 hashes. Each hash is taking around these many milliseconds. And remember, this is actually happening in the synchronous manner. That means until and unless the first hash computation is not completed, the second hash computation cannot start. until and unless the second is not completed, the third cannot start, and so on. One more thing to observe here is that this simple API call to this profile endpoint took around 2.3 seconds in order to get the response back, because this was the operation that was supposed to get completed before the response could be returned to this particular request. If I click on this send again, you could see that this request will keep on loading until all these hashes are computed. So the moment I click on send, it is processing. And this time you could see that it took around 2.45 seconds. And meanwhile, the server is computing these hashes. It won't be able to entertain any other incoming HTTP request to it. And in order to, you know, demonstrate this behavior, what I'm going to be doing is I am going to be replacing this 10 with 50 so that we get sufficient time to send multiple other requests to the server, just to demonstrate that even the other requests have to wait for this particular request operation to get completed. Now, since we have made the change here, we will have to restart our application. I will restart this application. I will close this and I will open this in a new tab. So the moment I click on profile button, it goes to processing. And if I click on send here, the about, which is independent of this hash operation, even this request has to wait for this previous processing to get completed. And you can see that even this request took around 9.08 seconds to get the response back, whereas the profile took almost 11.85 seconds. Now, this is going to be a significant performance hit for our Node.js application, right? So in this example, we saw that each hash is getting calculated sequentially on the main thread itself. And during the execution, no other request or event can be handled. And this clearly demonstrates how synchronous code blocks the event loop and it degrades the performance in a real world application. So we just saw that how a synchronous operation can block even the other request processing, leading to significant performance impact. We can actually resolve this problem by using the asynchronous version of the same code. Let me quickly replace this synchronous version with the asynchronous version. So what will I do is replace this code with this one. Okay. Now this time you have to make this observation that this function name, that is pbkdf2, is not appended with the keyword sync. That means it is not the synchronous version of this operation. That means it is going to perform this operation in asynchronous manner, or you could also say non-blocking manner. Okay, so since we have made changes, we have to also restart our server. But remember, since this is an asynchronous operation, this response.end is not going to wait for this asynchronous operation to get completed. So how do we make sure that this response is only returned when all these hashes are already computed? Firstly, I will change this number from 10 to 50 so that we get to see the same behavior as we saw before. So what will I do is I will cut this statement from here, and within this callback function itself of this pbkdf2 method, what I'm going to do is I'm going to add a condition where I would say that if the value of I is equals to 49, we could also say greater than equals to 49, but for now I could say 49. In that case, I am going to send the response back, because only by the time the value of I is going to be 49, then this response will be returned. Okay. Of course, there are better ways to achieve this. We can also even use async and await. But for now, just to keep it simple, I am using this simpler approach just to show you that this is how it could actually be done. Okay. And after making these changes, we will have to restart our server. Looks like this console.log statement has come twice. Let me delete it. And let me restart my server as well. Now, there are two observations that we will have to make here. One, the response time even for the profile endpoint will reduce significantly. The other observation we will make here is that while all these hashes are getting computed, even though the overall time that it will take to compute all the hashes will significantly reduce, but even in that particular duration, if some other request comes to this Node.js application, will it wait for this operation to get completed before responding to those requests, or what will happen? Well, since this is the asynchronous version, the other requests that are coming to the server won't have to wait for this processing to get completed. If that process can be served immediately, that request will be served immediately. We shall be seeing that. So, firstly, let me show you that if you go to profile, let's first look at the total time that it will take to compute these 50 hashes this time. If I click on send, then it is computing these 50 hashes, and this time it only took 3.93 seconds. Last time it took around 11.85 seconds or something around that number. If I hit that once again, then let's see how much of time will it take this time. This time it took around 4.37 seconds, but even it is significantly lesser than what we were observing in the synchronous version of that particular function. Now, since this is taking around 3 to 4 seconds, we would want to see that what happens if in between these 3 or 4 seconds another request arrives at the server. So I click on this send, I come here, I click on send. You could see that this response is gonna come immediately, even before these hashes are getting completed. So if I click on send again, the hashes are getting computed. If I click on send here multiple times, this request is gonna come. This is not dependent on the computation of the hashes that are getting computed because some other request initiated that. Why is it all happening? Because we just use the asynchronous version. All right. So this version uses the asynchronous PBKDF2 method of the crypto module, which actually offloads the hashing work to the libuv thread pool. The main thread in this case remains free to handle other events or incoming HTTP request. This is the preferred approach in production grade Node.js applications. In addition to that, I would like you to make an observation here. When we run the async version, we could see that only 4 hash operations are processed concurrently. So if you look at the output here, the first 4 hashes, 4, 1, 3, 2, now since they are happening asynchronously, you cannot predict the order. But one thing that you can predict here is that the first 4 hashes, they took around 261, 271, 322, 325, on an average probably 275 to 80 milliseconds was the time that was consumed by the first 4 hashes. And if you will look at the next 4 hashes, that is 5, 6, 7, 8, the next 4, they almost took the double time of the time that was taken by the first group of 4 hashes. And the same behavior can be seen for every other group of 4 going forward. This 9 to 12, this also took significantly more time as compared to the previous group, and so on. Now, why this happens? Well, this is because Node.js thread pool, which handles these offload tasks, has a default size of 4. We also discussed about this. So what happens is the first 4 hashes, they run in parallel, and the remaining 46 hashes computation, they are actually queued. And as soon as any thread become available, the next queued task begins or starts getting computed. And the completion time reflect this queuing effect in group of 4 that we have already observed here. All right. So to summarize, always prefer asynchronous methods for CPU or IO based operations in Node.js. Most built-in modules like crypto, FS for reading, writing, etc. Offer both synchronous as well as the asynchronous versions of the utilities or the functions that they provide. And using the async versions ensure that the event loop stays responsive and our application scales efficiently, and even the performance remains optimal even under heavy load. So that's all for this lecture, and thanks for watching.